Okay. Now, upon the challenging the reporter from the problem. 1 minute.
We would like to challenge the reporter for problem 4, shooting over men.
The reporter the reject
He was in
challenge. 4.
I will accept the charge.
Okay.
The correction of the reporter. And write down your name on the board. You. Time stop. Presentation of the reporter. 12 minutes.
Hello everyone, this is Tim. I'm the reporter to show the problem number 4, the shooting rubber band. And this is our problem statement. A rubber band may fly a longer distance if it is not uniformly and start when shot, and giving its speed. And we're going to find the longest distance of this rubber band can show. And our main focus is we're going to find the farthest distance, and we're going to discuss the speed of the rubber band. What caused the speed and how will the speed cause? And when the tension on both rubber band sides is different, it will cause the speed. And when the rubber band shot, the spin can make the rubber band be stable, so it can fly further. And this is our theory. We think the rotation on the rubber band will cause precision, and which will keep the rubber band stable and not to shake, so it can fly further. And when the rubber band rotate in high speed, the pressure on both sides will be different, so the rubber band will turn into other side. And this is our experimental setup. We use the things to let the rubber band be shoot, and the height of this experiment with this thing is about this height, and our rubber band is going to pull into this and the rubber band, the perimeter of the rubber band, this and this is the less like this. And this is our data for the rubber band shoot. The L means the difference between the rubber band on right hand side and left hand side. And the X means how the distance we shoot. And we can find out that when we get it to go, we can find out that is log L equal to 0.2581 log X plus 1 plus 1.7804. And when we learn to this, and we can find that it's nearly like the X, we can take this equation to the X is equal to A times L power of 1 by 4 plus B. And in this rubber band, the limited L is 15 cm. So we can find that when the L is 15 cm, the X is about 120 cm. So and the 120 cm is the farthest distance in this experiment. And now I'm going to talk about the turn in the y-axis. We consider that the x is for the distance we shoot, and the y is for the turn. And the y by x is the tangent theta that it will turn. Because of when the rubber band is spinning, and the right hand side and left hand side will have a different pressure, and will have a different pressure, and the pressure will cause the rubber band to be turned. And we can find that when the difference between the right hand side and the left, the tension between right hand side left-hand side is bigger. Okay, and the tangent theta that the rubber band will turn will be bigger, and will this change our result? We think it's no, because the tangent theta is very small. So we found that the tangent theta is very small. So I think it won't change our result. And this is our conclusion. The non-unfriendly rubber band, unfriendly restricted will keep the rubber band stable and fly forward. And the rubber band rotate in high speed will cause defective. And the relational expression between L and X is equal to A times L power of 1/4 plus B. And what is our farthest distance that we found is 120 cm is because the L in this rubber band the maximum is 15. And we found that when the rubber band is rotating, it will cause the turn. But we think that the turn can be ignored. And this is my whole presentation. Thank you for listening.
Okay. The question upon the reporter answer of the reporter. 2 minutes.
Okay, so firstly, can you switch back to the page you mentioned, precession? You said you observed that the rubber band has a certain precession. Can you define precession? What is precession? It means that the precession means that the axis of rotation changes when it is flying. Do you mean by that?
Because when
Yes or no? The axis of rotation will change when it is flying. Yes or no?
It will not change. This won't change but it will if you don't have the differentiation.
Okay, thank you. Next question. Can you switch back to the data analysis page? Where does your fitting curve come from? What does it mean? Why do you use the log graph? Why do you use the logarithm?
To find the x.
Okay, thank you. And the next page, you used the exponential to fit the data. I'm not sure where it comes from. Is it from your?
This is at the.
Is
this? I just drew it into the.
Can this fitting be explained by a theory? Yes or no?
Because the.
Yes or no?
Our theory didn't have the equation.
Okay, thank you. And do you consider the air resistance in your theory?
Yes, but because our theory didn't have any of them.
Okay, thank you. Can you switch back to your experimental setup? Do you consider your experimental setup parallel to the ground? Is your setup parallel to the ground?
This is a ground and this is.
Stop.
Thank you.
Presentation about 3 minutes.
Oh, sorry. No, preparation.
I stop. The opponent check the flow. Make the 4 minutes.
Okay, this is the opponent from the Team Miracle. They're opposing shooting rubber band. So for problem recap, the problem states that a rubber band, when it is can fly a longer distance if it is non-uniformly stretched, and we need to optimize the distance. So in my opinion, we firstly need to define non-uniform stretch and spin, and then we study the factors affecting distance, and then discuss the maximum distance a rubber band can reach. So for general pros and cons, we think that the reporter has a well-organized report, but they don't have a quantified theory, and they compared measurements. But as for cons, they don't have any intuitive explanation for this phenomenon, and they have fuzzy terminologies and definitions for spin, pressure, and non-uniform stretch. They missed an important parameter called initial length because we observed that you did non-uniform stretch, and the stretch difference, the length difference between the two sides of the rubber band, but we don't see the initial length parameter in your experiment. And then we think that you lacked quantified theory to explain your experiment. And we think you also lack comparison between different measuring methods. For report overview, for preliminary experiments, we think that you observed non-uniform stretch. But you defined precession and you defined pressure, but you didn't explain deeply about it. So we didn't quite grasp what did you mean. And we asked about whether is your setup parallel to the ground, and you didn't give a clear answer about it. So we think that in this preliminary experiment, you get a clear observation, you get a key feature of the non-uniform stretch, but we didn't see clearly of your setup. So we would discuss with you later on. As for the modeling, we think that you maybe assumed the isotropic and you maybe cited for application law, but we didn't see much of your modeling. So that's a point to be discussed later. Next. As for experiments and analysis, you did the parameters for stretch and non-uniform stretch. You analyzed it with log plot, double logarithm plot and exponential plots. But we didn't see the comparison between your theory and experiments, and we didn't see the reasonings for your fitting of your data. And you concluded with the distance of flying increases exponentially with the difference between the two lengths of your non-uniform stretch. So for discussing points, we think we want to discuss with you later on the modeling part. We think the importance of air we think the air resistance is an important parameter. And then because you mentioned there is some precession in the rubber band, we think that rotational kinetic energy is also an important parameter. And then we think that initial length also will affect the potential energy stored in the rubber band. So we think that it is also an important parameter to do experiments. As for setups, we want to question you, how did you release the band? Whether you did it parallel to the ground. And we also want to question you, how did you maintain the non-uniform stretch? And how do you define your precession? That's the point I want to discuss with you later. Okay, that's probably it.
Discussion.
Okay, so the first question, I want to ask about your setup. Can you switch back to the experimental setup page, please? You define the non-uniform stretch as the difference between the two stretching lengths of the rubber bands. Yes, and because the problem says that by non-uniform stretch it will fly longer, and we think by this statement it must have by non-uniform stretch it must contain a lot more of potential energy. So if you were to maintain non-uniform stretch, you need to provide some support for it. So how do you maintain your non-uniform stretch if it will automatically get back to the initial condition of uniform stretch? How do you maintain the non-uniform stretch?
I just put here and I use the glue to get the line and put here and select over. So it won't go back to the this at the finger.
So you pin down the 2 points on the rubber band and then stretch it out.
Yes.
So that in such a way that it won't go back to its initial condition.
Yes.
How did you do that? How do you pin it down? I'm not quite so sure. Can you point it out to me?
Here I just that one here and that the long part I want and put here and pass it.
So you use your hand to release the rubber band, or not? Okay. So how do you control the time when you release the rubber band if you use your hand?
I don't need the time.
So
Just
because
just go.
yes, because if you release the band manually, your hand has a length. So if you hold rubber band if you hold rubber band originally in here, as you gradually release the finger, it will slide across your finger. So it will cause friction. How do you? If you try to shoot rubber band like this, then you hold the rubber band between the thumb and the index finger, and when you try to shoot it, firstly, if you try to shoot it, it will try to slide. So it will slide across your thumb. If you use your hand do you observe the phenomenon?
Yes.
Yeah. So how do you control it? Okay, next question. If you release the rubber band manually and you pin it down on the other side, how do you make sure that the rubber band hits? How do you make sure that whether the rubber band hits the other pinpoint?
It won't hit because the other side didn't use my finger. I just put up.
Okay. Okay. Next question. Okay. So is your setup parallel to the ground? Have you measured it? Because you mentioned that you measure the distance between your launching point, and then the points where the rubber band falls to the ground. You measured the distance between these two, right? But as you know from the free fall or experiment or something, you know that the launching angle of any object will affect the distance.
Yes.
So do you control it?
Yes.
So you control it, but how do you? Okay.
I
How do you control it?
check the angle.
You check the angle every time before you
Yes.
launch the rubber band.
Yes.
Okay. 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 So nextly, I want to discuss with you the theory of the theory and modeling of your experiment. You define pressure and precession. Firstly, you define precession. So can you elaborate more on the precession of the rubber band? Do you have a video for it?
First, because the rubber band, when the rubber band shoots, moves very fast. Although we try to use the slow move to check if it is spin or what the spin speed is. It is, but it just moves so fast, so we cannot track it.
So how can we be sure that it is indeed precession if you can't capture the whole motion of the rubber band?
But to see when we see the slow motion video, Though it was going very fast, but we can still see the rubber band because the rubber band I have a black mark at the rubber band, so I can see the weapon is going like rotating, but it's too fast to.
Okay, so in order to measure, in order to observe the markings on the rubber band, you must have shoot it from the upper side of the rubber band, right? In order to observe the rotation of the mark, you shoot it from the upper side. But when you shoot the rubber band, it will. If you didn't control the initial conditions properly, it maybe will spin, and it won't be perfectly parallel to the ground when it is flying. So how do you make sure that the rotation, the angular velocity of the marking, is actually on the plane of parallel to the ground, not like tilting or something? How do you be sure?
I cannot sure that, but it's not matters because if I shoot at this and it will be like this and don't change very much.
Okay, I see. Then nextly, at the second pinpoint of your presentation, you define pressure. What do you mean by pressure?
Can I repeat that?
Can you? Yes.
Because
This I can.
because
Thank you.
because when the rubber band is rotating in the air,
Yes.
and we can know that it's going up, and the air will go through here and here.
Yes.
And when it is rotating, this here, the velocity will be bigger, and here will be smaller.
So try to use the
So the second is the other pressure.
so you try to use the air pressure difference on the two sides of the rubber band to say that yes, it will fly farther in this scenario.
Yes.
Okay, that's a we didn't think about it before. Okay, for pressure differences that causes rotation, we think that maybe because rubber band is elastic, so maybe you can try to consider, because you mentioned tension in your presentation, so maybe you can cite Fouquet's law to try to build a theory, and you can using Fouquet's law and assume that the rubber band is isotropic.
Yes, but the rubber band won't follow the photograph.
Why?
Because when you grow the rubber band, like you pull a rubber band, it is the first is here, and when you pull it, it will be like this, and
So you mean the cross-sectional area will be different?
yes, and the K is not constant.
Yes, and that is a thing to be taken into consideration. But Fouquet's law serves as a naive assumption for the rubber band, so you can get a glimpse of your theory about air pressure difference on both sides.
And the most important thing is when the rubber band was shooting in the air, it will not be like a perfect circle. It will be like
So in that condition, you
this
can.
or other than it
I
is
stop.
uneven. So
Thank you.
Now, I want to summarize the discussion.
Okay, so as for the discussion points, we discussed about the way to release the rubber band. The reporter, I asked about this question, and the reporter concludes that they use hands. So we should consider friction in this scenario. And they have checked the angle of the rubber band. It is fixed every time they release the band. And the capture of the motion, they use a mark on the rubber band to capture, but in that condition we can make sure the angular velocity of it. And nextly, as for the model, they considered air resistance as a form of pressure difference, so that it will fly it will fly a larger distance because of velocity on the two sides is different. And they don't think rubber band will fit the case law. Thank you.
Okay.
Hi, I'm the reviewer, and this question is for the reporter. So, in your demonstration, you said there will be a pressure, and do you think the pressure will be big enough to make it actually move sideways?
In our experience, it's truly turn.
Okay.
So
Okay, thank you. And as the opponent mentioned, you said the reporter should consider air resistance, and do you think the air resistance will be big enough to affect the results?
Air resistance is related to the air pushing is resisting the rubber band from moving. And he mentioned the air pressure difference, but I don't think the air pressure difference is big enough. But
I mean, the air resistance, is it big enough to affect the results?
I think the air resistance should be taken into consideration.
Okay, and do you think there is a boundary condition when you use Hooke's law to analyze the rubber band?
If the rubber band deforms too drastically into a plastic condition, then the case law does not apply.
Okay, this is a question for both of you. What is the most important parameters for this experiment, elongation or rotation? You can answer first.
I think it is elongation.
I think it's rotation.
And why?
Because the rotation will cause the resection and it will be stable and you can fly from it. Because if you don't rotate, it will like unstable and it will like rotate like shoot and rotate like this and it will not fly very far.
Okay, I understand. I have a question for both of you. Do you think there is a critical initial height if you want to optimize the distance? Could answer first.
I don't think there's. What do you mean by initial height? You
Like
mean
the height of the launcher.
according to the tossing motion of any objects, that will indeed affect. But optimized heights, I don't think so.
So you think there's no critical height for the best distance?
I don't think so.
And what does the report think? Okay. Do you think there's a critical launch angle for this?
I think there is a primary launching. There's a primary launching.
And is it parallel the best or not?
We don't think it is the parallel is the best.
Okay. Do you think there's a critical launch angle?
Yes, I think it is the vertical launch angle, and I think it will be
Don't
lower
stop.
than 55.
Okay. Thank you.
Preparation from the reviewer, 2 minutes. Time stop the reviewer take for 4 minutes.
Hi, I'm the reviewer from Team Relativity, and the problem statement says if the rubber band is not uniformly stretched, it will have to fly longer distance, and the reporter should optimize the distance that it will fly. So in the theory, he explained about the rotation of the rubber band, the precession of the rubber band, and Bernoulli's principle effect is moving sideways. In the experiment, he has a rubber band, and he made the launcher himself, and then parameter is the elongation and angle. And then the reporter, I think he has a very quantitative phenomenon explanation and a decent launching setup, but I think he lacks some physics picture for this phenomenon, and then he maybe could find an equation, an expression for the distance, and then I think he could have also done more experiments, and then so in some of his decimals chart, he lacked the labels for it. And for opponent, I think he has a good and clear remark, and then asked a fair amount of key questions, and then he showed how to shoot the rubber band himself, which is a good demonstration, and I think he didn't let the reporter understand some of his questions, and he's a little bit too aggressive. And here's, I think, is a missed point in the discussion. So I think it should talk about air resistance because the reporter and opponent has a disagreeing about if the air resistance will affect it by a lot, and then about how measuring the distance properly. So if we shoot the rubber band, sometimes it will bounce on the ground, and the reporter didn't mention it's like the first touch or after a few bounces. And then the spin and effect on distance, and the magnus effect. When you shoot it vertically, it will fly longer. And here's the discussion. So the opponent asked, please define the precession, and the reporter didn't answer clearly. And I think precession is not in this phenomenon because it needs to be on 2 axes spinning, and I think there's only 1. And the opponent asked, can a decimal sign be used? And the reporter said no. And I think agree with the reporter, but he should find more equations to actually use the lines. And then the opponent asked to find a uniform stretch, and then the reporter said use ruler to hold the shoot with his hand. And I think he maybe could add something to his launcher to make the shooting more consistent. And then the opponent asked does the launch angle affect, and the reporter said it will. And then the opponent said, please set, how to set the angular velocity for a rubber band. And the reporter said he doesn't have a clear way to set it. And I also think he can improve the setup, maybe include some place to hold the different elongations of the rubber band. And then the opponent asked to find an air pressure, and then the reporter draw on the board said it will move sideways. And I think it wouldn't because on both sides of the rubber band the pressure would be the same, so I think it will still fly in a straight line. And then the opponent said, why couldn't use the Hooke's law? And the reporter said because of experimental data, and I think in certain conditions the Hooke's law can be used in this phenomenon when it's not elastic on a rubber band. And then I asked is the air resistance big enough to affect the results? The opponent thinks it will, and I think it's very small to actually consider it into a real model and would be very hard to calculate. And I asked, can you use the Hooke's law in this phenomenon? And the opponent said you could, and I think I agree with it because there is a boundary condition for the Hooke's law. And I asked the reporter what's the most important parameters, and he said rotation, and I agree because when you give it a uniform stretch, you'll have more potential inside the rubber band, which will make it fly longer. And so I think it's correct, and also a problem statement states that it will. And I asked the opponent, he answered elongation. And I think even though the elongation is important, but if you stretch it uniformly, it will have more potential. And that's my
Let's conclusion remark of the reporter. 2 minutes.
Hello everyone, this is my conclusion remark. With the presentation, by report we have to name what is it and also sign the unit on each axis or on our data. And also we did not put the video of this experiment. And also we should get our theory more deep to get the equation of the max distance. And And the experiment, we have to make more experiment to ensure our theory is enough to prove our point. Also, have to consider other parameters may affect how long the rubber band can reach. And I think we should also do other kind of the rubber band to get the longest distance and try to find the longest distance between different kind of the rubber band. And this is my conclusion remarks. Thank you.
Okay. Now, the question of the jury.
Just one question on the focus. I think in the rubber bands, right? So you use the same rubber band to do the experiment
Yes.
all the time.
Yes.
Even you give the highest stress
I
on this one. Did you ever try different rubber band? And also somewhat, I think you have mentioned the hook control, right?
yes.
What do you think? Have you used just only one stress, or you have using the many rubber band?
I use one rubber band to do this experiment, but with one L numbers I do 3 times and get a average. So and just do and we got a maximum
Okay.
of this rubber band, but I didn't do
Okay,
other
thank you.
experiment.
Yeah, so I also ask the same question for opponents. Do you think that you have to use in just only one, or just the same one? When you do the experiment, is there any reason to make a difference?
I think that if you use the same rubber band every time, it will cause it will be out of the Today's law range. It will cause elastic. I don't know.
Yes. Yeah. Okay. Okay. So how about your comment?
When you buy some rubber bands from store, each rubber band is a little bit different, so I think you should use only one rubber band and make sure it's not elastic fatigue. And also, in every use, you need to rest it in the same place for around like 5 minutes to make sure it's elastic constant gets back to the same.
Yes, I have finished.
Okay, that's enough. That's enough. Thank you.
Juries?
So, for the opponent, you asked about the procedure. Yeah, for this body, when it moves in a projectile line, there is not possibility to add any torque. And in this system, it seems to be some kind of inner force because of the elastic energy. So, can you shortly explain what is your opinion about this procedure, the origin of this procedure?
You mean when a rigid body is moving along?
Yeah.
And
you cannot, yeah, because you cannot transfer torque. So, may you explain your why you suggest that there should be a precision in this rubber band?
I think that the rubber band is when it is flying, it's definitely the mass is not uniform because it is stretched non-uniformly, so the mass is not uniform, and then the rubber band will definitely not be axial symmetrical. So I think that by symmetry and non-uniform mass, the inertia tensor will be in different directions. So I think because of the inertia tensor things, the direction of the inertia tensor and the angular velocity, I think that there will be precession. I don't know how to put it in words.
So for the review.
Because I think the rubber band is very different from a rigid body. It's very elastic, so I think I don't think there's precession in this amount.
Okay. There is a jury problem? No? Okay, now keep the scroll. Ready? Okay. Now we show the report, the scroll. 4, 4. Okay, no. 4, 3, 4. Thank you. The next show the opponent. Add 6, add 6. Okay. Finally, we show the reviewer. Add 7, 6. Okay, thank you. We finished.